Howdy folks, and all the wonderful subscribers. It's me again, your Chief Marine Mate Eddie. In this segment, we will be discussing about gas carrier ship, their cargo, and how they are being transported, including its containment system. And before we start with anything else, if you have not subscribed yet, kindly click on the subscribe button and notification bell, and click like if it pleases you. Let's begin.
Foremost, we knew about petroleum gas and its usage are just a common thing, though majority will only think of as it is being used for cooking and heating, which is very true. But when we talk about how it's being transported, usage or application in a broader view, then such curiosity may differ from one's interest. Of course, who cares anyway when you benefit from it? It won't bother much except when your bills arrive after using it. Nevertheless, let's expound and explain it, and you may just wonder where it came from, how it's being transported, and finally, to know its major impact to our world's energy demand. To start with, gas carrier ship transport the bulk of these gases in liquid form. Yes, in liquefied state. The obvious is clear. Most gases can be transported from its natural state in volumes to about 700 times less ratio when it's liquefied. This means it can be transported with huge amount from one point to another, coast to coast, all through the world trading routes. The other means of transport will be then carried through pipelines, inlands, or submerged under seawater marine pipes that crosses distances. And thus, it's delivered into your homes or industrial entities for energy consumption. Majority of these gases are the byproducts extracted from fossil fuels. Yes, fossil fuels, mined beneath the Earth's surface, drilled or bored through inlands or seabed where such precious commodity came into existence millions of years ago. We can term this as raw crude oils and natural gas trapped in a reservoir in different places around the globe. They go through a process where we term it as cracking, fractionation, and distillation in refineries close to major sources. Hence, the outcome yields different byproducts ranging to many types of petroleum oils, petroleum and chemical gases. Since we are focusing on gases, these are basically the lighter density yielded by the fossil fuel when refined. It becomes your propane, butane, ethane, and methane, where the latter comes directly from a natural gas reservoir. The other byproducts are chemical gases, where they are cracked and mix up with other substances to form other petrochemical gases such as ammonia, BCM or vinyl chloride monomer, chlorine, amongst many others. This group also includes such hydrocarbon gases such as ethylene, propylene, butylene, and butadiene. Under normal atmospheric temperatures and pressures, all these compounds are gases. This is their very common properties. However, they do differ with transportation and handling procedures because such compounds behave at different temperatures and pressures. Liquefied gas carriers use a variety of cargo containment systems. Depending on the characteristics and properties of such compound, each has its own specialized containment designed specifically for it. This is determined by the temperature and pressure, once again, required by the cargo, and likewise the cost of shipbuilding to contain and sustain it. Although these compounds are all gases by nature, the reactivity to both materials and with other substances like chemical gases will of course restrict the design for such carriage or transportation. To give you a better view on how you may see or observe in layman's understanding, let me show you a graph of the physical and thermodynamic properties, and let's get down into details. As shown in this graph, which is commonly called vapor pressure diagram, the vertical baseline on the left represents the pressure. A corresponding value in perpendicular line with color-coded blue is the value for the pressure. The horizontal baseline is the temperature in degrees Celsius, corresponding to the perpendicular vertical line in color-coded red. For the purpose of this discussion, we shall use the unit of measurement as kilogram per centimeter square, or equivalent in bar pressure or normal atmospheric pressure. For convenience, this is generally expressed as the saturated vapor pressure or SVP in a non-linear scale. We see in here the type of gases mentioned earlier. Each gas has its own individual curve on the graph. Its SVP or saturated vapor pressure is the pressure exerted by the boiling liquid vapor of the gas within a closed container at a given temperature. The condition when the gas becomes a liquid and the liquid can become a gas. These are the curves for other common liquefied cargoes: butane, BCM or vinyl chloride monomer, ammonia, propane, propylene, ethane, ethylene, and methane. Now let's take a look at this example, the curve for butane. So under conditions, to the left of the curve, butane is a liquid, and to the right, it is a gas. Hence, at 0 degrees Celsius at 1 bar, butane is a gas. 1 bar, absolute, is the equivalent of a 0 gauge pressure. If we go up the curve, we can see that the pressure of 3 bar is enough to keep it a liquid at temperatures of up to 30 degrees Celsius. To demonstrate, let me show you an easier explanation using this cigarette lighter. It has butane inside, sealed in plastic disposable container. The gas itself has a boiling point temperature of -1 degree Celsius, but since it has been contained in a pressurized containment, by law of thermodynamics, boiling point temperature is directly proportional to pressure. The same will happen when you are cooking with a pressure cooker in your household. The boiling point of water becomes higher than 100 degrees Celsius, whilst in open container lid, it boils at 100 degrees Celsius under normal atmospheric pressure. So as you can see, the ambient temperature and atmospheric pressure will determine its behavior within its containment. The liquid butane will be subjected by the ambient temperature and pressure. Thus, the vapor will become equal to ambient temperature. It will stop evaporating, or the liquid stop boiling off once the vapor equalizes to the molecules that tries to escape against the molecules that turns back to liquid. At this stage, we call them as saturated vapor pressure. If we release the pressure, the gas will start to go out, and hence the liquid starts to boil off again, as demonstrated in this segment. Basically, this is exactly what happens represented by the graph. As shown, the pressure drops and the liquid boils and yields gas or vapor. This is the same property also or behavior you will find with propane, as shown in this graph. We see that in theory, it could be carried at atmospheric pressure if it is kept below -42 degrees Celsius, or it could be carried at temperatures up to +40 degrees Celsius if it is contained in a pressurized vessel, or kept at a pressure of 10 bar or more. However, gas like methane, which is a natural gas, we see that will always need to be refrigerated as even at a 40 bar pressure. It must be kept below -80 degrees Celsius to remain a liquid. Although at this present times, we now have a technology to contain them without refrigeration by using CNG or compressed natural gas. However, in this condition, methane remains as a gas and or transported as a gas but not in liquefied form. These are now applicable to some transportation vehicles where methane is used as a fuel for their engine. Sometimes mixture of gases are carried. The SBP of the mixture will depend on the proportion of the two gases in it. Mixture of gases, provided they are both saturated hydrocarbons, for example, propane and butane, or ethane and methane. The curve will lie somewhere between those of the separate gases. The other gases may not be mixed since some of them are unsaturated hydrocarbons, which means their molecular components are unstable, e.g., for example, ethylene cannot be mixed with methane. Chemical reaction will occur and a hazardous situation may come out as a result. Now let's talk about how they are transported. In what condition, type of containment, and what are the building materials used. Gas carrier ship evolves originally from oil tankers, but it differs a lot when it comes to design and cargo operational procedure. In oil tankers, the cargo tanks are mostly an integral part of the ship's hull, while in gas tankers, the cargo tanks are always separate structures or independent. In short, the containment or cargo tanks are structures within or inside another hull. Let's just say a tank inside a tank. As seen with the comparison in this image displayed, literally, the ship's hull and most of its structure are built up in one place, such as in a shipyard, while the cargo tanks are separately built based on the type of cargo, and hence it is incorporated or put in place or loaded as a whole or assembled within the inside of another hold or void spaces while the ship is being constructed in a shipyard. Such design must conform with gas codes or the so-called IGC, International Gas Code, developed by IMO or International Maritime Organizations. They are carefully laid out in details as with any other ship, but most of all were determined to meet the specification required for such cargoes. Containment systems are tested with a great deal of importance to make sure it will have to withstand the large thermal stresses provoked by cooling down and loading in preparation for dry dock, gassing up, inerting, warming up for gas spraying, and so many other cycles of operation on board gas carrier ships. So, the question arises, how are they being transported based on the previous explanation of their behavior, characteristics, and properties? By standards, there are two major modes of transporting condition depending on the cargo. Number one, cargoes are carried in fully pressurized vessel, just like your LPG bottle tanks in your households, but of course in a bigger size and it floats in the sea. Number two, cargoes are transported in a semi-pressurized and fully refrigerated vessel. And number three, cargoes are transported in a fully refrigerated vessel. For liquefied petroleum gases or LPGs, number one item are most applicable on the usual propane and butane or mixture of both. However, this ship has a trading routes close to the shore or coastline, short distances, and less amount or capacity to carry. Number two item are utilized for cargoes that yields a higher pressure and lower temperature, such as ethylene. These cargoes should be contained in a semi and robust pressure vessel, but capable of reliquefying back the liquid. Hence, the so-called fully refrigerated type is applied. Thus, the pressure are basically just close to zero gauge pressure or atmospheric pressure. Number 3 type is the fully refrigerated, which is basically same principle as item number 2, but less pressure of cargo. Basically, this is the same cargo as the number 1 item, except that it carries a large quantity of cargo. Tanks are bigger because they do not need to be fully pressurized. In short, The steel tank thickness is thinner but bigger, and so they can create a bigger vessel, and it carries cargo at atmospheric pressure. For the liquefied natural gases or LNGs, item number 3 applies. Nowadays, both are carried typically with a reliquefaction system. Hence, the vapor can be extracted from the tank top, goes through the liquefaction system, and injected back to the tank and goes in cycle. While the typical type or original ones, the boil of gas will be released and diverted to the engine room to be utilized as an engine fuel. So, if we look back at the diagram shown in the earlier part of this discussion, we are basically bringing down the pressure, and hence the boiling point of such cargo also will go down. Thus, it remains as liquid, less than the vapor that was utilized for the engine fuel. For chemical gases, all items 1, 2, and 3 in the mode of carriage can be used. However, the materials as well or the containment may varies. This is in terms of chemical reaction or reactivity to the material or structures. In general, the type of cargo will be stipulated in the Certificate of Fitness or COF, meaning most ships specifically designed for such cargo won't likely to be able to load any cargo they want. So basically, they are intended to what they are designed for. So let me tell you with a typical type of ship for LNG with a spherical type of containment. And this will be followed by a brief description of the category of carriage and containment type. Okay, let's gonna tour you with the so-called LNG spherical type B ship. And as you can see here, we have 4 tanks. They are basically can be fitted with 4 or 5 tanks, and for the purpose of comparison, I have also included the oil tanker vessel beside it. Now, the sizes are not necessarily to be compared of. Some are bigger. For example, if you are talking about a very large crude carrier, it could be bigger than the spherical type. In this case, they are basically almost the same. So anyway, with no much further ado, let's start. As you can see, I am on the bridge and I'm looking at down below through the cargo tanks. So I'm just gonna go down and let's go down the stairs. Right, so basically we are now on the top of the spherical tank containment system, and you could see the pipes. This pipe goes all through the way to the engine room. This is the one that I am talking about a while ago. If the vessel is not fitted with a liquefaction plant or a liquefaction plant system, then the vapor that boils off from the tanks cannot be reliquefied and be injected or condensed back into the same tank. So what happens is that instead of releasing them through the vent mass, which is of course a precious cargo, they utilize it as a fuel for the engine of the ship. The engine of the ship is a dual fuel, so it can run in diesel, bunker, and also it can run with natural gas. So typically, this is the first type of model or vessel of LNG carriers in the early days. So as you can see, we are just almost in the middle. Let's go down. Right, so they are really very large containment tank, and it can carry out about more than 135,000 cubic meter. of liquefied natural gas. So it's really huge and big. Alright, that's the manifold area. That is where the manifold arms connected when they are loading or discharging. So they are connected in these areas. Right, so this is just a brief tour. Let's run a little bit so that you will see further what's in the forward part. Of course, there are winches, anchors, windlasses, and other equipments like Panama beads. Those are for the mooring equipments, etc. Now, as you can see, compared to the oil tanker, it's quite pretty spacious, and there is not much of the pipe, because in gas carriers all pipes are actually should be above deck. Unlike oil tankers like this one, some of the pipes can even run all through the tanks, and it passes through some tanks, like for example for the very large crude carrier. Of course, some tanks doesn't have that kind of design or fittings, wherein they have individual pipes for each tank, especially for the chemical tankers. So right, yeah, this is the spherical, and I'm gonna show you the rest of the containment system of LNGs. Okay, these are the different gas carrier containment systems. As you can see, we have the 4 major types of LNG carriers nowadays. We have the spherical type, the membrane type, and also the IHI type. So on the gas carriers for LPG, we have the so-called independent type A, this one, prismatic, and the independent type C, cylindrical. So to give you an overview, it looks like this in the inside. So as I mentioned earlier, apart from the shipyard building the whole entirety of the ship, the tank is also, of course, being built, and in most cases they are built by another maker or a manufacturer like GTT, Gas Transport and Technigas. And if you notice, inside of the tanks there is no bulkheads or the dividing wall in layman's term. I can explain that later in other discussion. Right, of course, we have also the not so popular but very efficient SPB. As you can see, it has a bulkhead. That means to say it has less stresses, and at the same time, when it comes to the so-called sloshing, of cargos, it will be lessened, of course, because it has a bulkhead, and also further minimize the effect of free surface effect, as we call it, which is basically adds up to a so-called negative GM. As you can see, they are loaded as a whole while the ship is being built. And of course, we have the spherical or Moss Rosenberg. Looks like this in the inside, and there you go. That's the one that I have given you a tour a while ago. So that's inside the tank actually. First you have the cover steel and the large dome that you have seen, and then of course inside are the insulations and aluminum tank shells, and then of course your primary containment is steel or aluminum inside. And the sides, of course, are your ballast tanks. This is where you carry your ballast tanks, and that's typically what I've shown earlier. And another picture, that's inside of the tank of the spherical. So yes, they are categorized in independent, which they call it as type A, type B, type C, while the other are the most popular are membranes, which is of course the GTT Mark III, number 96 and CS1, and of course the type B spherical type, this one, the most common and majority LNG that is being used this present day. They do have, of course, different requirements, but in most cases they have a general requirement. Each of them has containment that is capable of containing total arrangement for containing cargo, including where a primary barrier is fitted, a secondary barrier also, and then associated thermal insulations, and also intervening spaces and adjacent structure to support the elements. Anyway, just to sum it up, this is the kind of containment of cargo gas carrier.
And so this concludes our topic for the introduction of gas carrier ship. In the next episode, we will be talking about the operational procedure or cargo operations on board liquefied petroleum gases. And each sequence, we'll tackle them one by one, so keep posted. Thank you for supporting this channel. See you again.